If we can recall the RS flip-flop, if the set and reset both inputs are 0, in that case the output is the previous state. If the set input is high, then output becomes the logic high. And if set is equal to reset is equal to 1 and the set is equal to 0, then the output is 0. But the fourth case which we have, like if set and reset both inputs are high, then that becomes the indeterminate state, which is not acceptable, not required state. So how to avoid that problem? To avoid that problem, there is one solution, that you can use the delay flip-flop or the D flip-flop. So delay flip-flop is the alternative way to make it race free or the indeterminate state free flip-flop. Okay, so how we can make the D flip-flop? Let us try to see. So suppose I have RS flip-flop. Okay, and in this RS flip-flop, we know that we can have the four possibilities. Let's suppose I have a set and the reset input, so I can have 0 0 0 1 1 0 and 1 1, and accordingly I will get the qn. 0 0 means the qn plus 1 is nothing but is the qn. 0 1 means it is 0, 1 0 means it is 1, and 1 1 means it is indeterminate state. So this is what the truth table of the SR latch is, SR flip-flop is. This state is not acceptable, not required. Okay, and this state is not doing anything. If you see the first state is not doing anything. Whatever the state was previously, that will store the same logic. So it is not going to change anything. Okay, so these two states are not that much important. Okay, and because the last stage is not desirable and the first state is not required, because it is storing the same logic whatever it was before. Okay, so only the important logics that we can see here are the 0 1 and 1 0. And if you see these two things here, S and R both are complementary to each other. If inputs are complementary to each other, so these two are the acceptable state and that we can have in any of the latches. So what we can do? We can simply connect one inverter between set and reset, and we can call it the D input. So if D is equal to 0, set will become 0, R will become 1. So the output will become 0. So this output will be reset. If D is equal to 1, if D becomes 1, this S will become 1. S is 1 means reset will become 0. So output will become logic 1. So there is a possibility like 0 and 1 output I will get. I will not get the this indeterminate state. So this problem can be avoided with the help of D flip-flop by just adding one inverter between two inputs. Okay, so this kind of the resultant flip-flop, we can call it the delay flip-flop or the D flip-flop. Okay, so if what it means, let us try why we are calling it the delay flip-flop. Delay flip-flop simply means that suppose if I am giving input 1, so the S will become 1, R will become 0. So I will get Q as logic 1. So what was the input? I am getting the same at the output. Similarly, if D is equal to 0, so S will become 0, R will become 1, and R is equal to 1 means this will become 0. So whatever the D was there, I will get again at the output. So the input, whatever the output I am getting, that will be the same as the input, but with some delay, because there is some internal delay of this flip-flop. So that is why we are calling it the delay flip-flop. Okay, so of course, if this kind of circuit we have, then that we can hold the logic at the Q and QB. So this is how we can call it the flip-flop, and the delay, because input and output has the same logic but with some delay of this flip-flop, that is why we are calling it the delay flip-flop. Okay, so this is how you can make the D flip-flop. Now let us try to see that. Yeah, so this is what the QT and QT bar is there. So let us try to see how the characteristics table for this D flip-flop will look like. So I can have two possibilities for QT and two possibilities for D. Okay, so the QT can have 0 and 1 and the D can have 0 and 1. So we can have a total 4 possibilities, and that will be like 0 0 0 1 1 0 and 1 1. Okay, so let us try to see. If qt is equal to 0 and d is equal to 0, so the qt plus 1, I just told you, whatever the d I have, that will be reflected at the output. Okay, d is nothing but that is same as the qt, so this will become 0 1 0 1, and the complement will become 1 0 1 0. So this is all about how the characteristics table or the characteristic table for the d flip flop will look like. Okay, so if it is like that, let us try to simplify a few things, and let us try to see how it could be done. If I can solve this k-map for q plus 1, so the k-map will look like this one. How the k-map will look like, let us try to see here. Let us try to make the k-map for qt plus 1, where the qt and the d are the variables. Okay, so 0 0 0 1 1 0 1 1 is possible. So it could be 0 1 0 1. So this is what we are getting here, 0 1 0 1. And if you see here, we can make the pair of these two things. Okay, these two one can be made, we can make the pair of these two things. And if we try to simplify it, how the simplified version will look like, if we try to simplify, we are getting q t plus 1 is nothing but this is equal to the d. Okay, because qt will be cancelled out, and whatever the things we got here, this is nothing but this is the characteristics equation of d flip flop. So these equations are really very important. So the characteristic equation for d flip flop is nothing but this is the d. Okay, the next thing we need to see how the state diagram will look like. Okay, so let us try to make the state diagram. We can have two states at the output. Okay, what are those states? One state could be 0 and the second state could be 1. So these are the two states that are possible in the d flip flop. Okay, so let us assume I have a one state for output that is 0 and the second state of output that is 1. Okay, suppose I have a two outputs 0 and 1. So what happens if the qt is equal to 0? Let us try to see here. If qt is equal to 0 and d is equal to 0, so I am getting the same output. Okay, so what it means, I will get the same output if the d is equal to 0. If d is equal to 0, I will get the same output. Okay, next thing, if the qt is equal to 0 and d is equal to 1, the qt plus 1 becomes 1. So it is changing from 0 to 1, and the case is if d is equal to 1. So this is the case which is changing from 0 to 1. Now let us talk about a third case. If the qt is equal to 1, okay, this is the qt, this is the qt, and the d is equal to 0, so the qt plus 1 will become again 0. So the qt plus 1 will become 0. Yeah, so this is the fourth case. The third case will be this one, where we are putting d is equal to 1. And the last one, if you see, if the present state is qt, the next state becomes the that is 1, and the next state will become 1 if the d is equal to 1. Okay, so it will maintain the same thing if d is equal to 1 here. So I think I made one mistake, right? Yeah, 0 0 0 1. Qt was 1 and d is equal to 0. So yeah, so here it will become something like this. Qt plus 1 becomes 0 and d is equal to 1. Okay, so these are the outputs. Okay, so 0 0 0 1 1 0 1 1. So this is how you will get the outputs. Now let us try to see if we have the state diagram. Okay, if we know the state diagram, and if we want to make the excitation table, this is really very important, because one of the points which we discussed before, that is the excitation table. And excitation table decides, like, when you have to design a counter and other things, then excitation table play a major role. Okay, for now might be it is not that much important, but when you will try to design the counters, at that time the excitation table play a major role. Okay, so let us try to see how the excitation table we can draw. Okay, so the excitation table will be something like this. There are four possibility, qt and qt plus 1. So it could be 0 0 0 1 1 0 1 1. And if we see here, qt is 0, qt plus 1 is 0, qt is 0, qt plus 1 is 0. So this is coming when d is equal to 0. Okay, now let us talk about the second case. Qt is equal to 0 and qt plus 1 becomes 1. Qt is equal to 0 and qt plus 1 becomes 1, and the condition was d is equal to 1. Similarly, the qt was 1, this case qt was 1, okay, and the qt plus 1 becomes 0, and the condition was d is equal to 0. And the last case 1 and 1, and this becomes the d is equal to 1. So this is how the excitation table for the D flip-flop will look like. This is really very important table that is needed, okay, for the counter designing person. So this is how we can make the D flip-flop state diagram and the excitation table.